Okay, thanks, Yuval. So thank you, Yuval, and the other organizers for giving me a chance to participate in what I found to be a very stimulating conference and in this very beautiful place. I've really been enjoying my time here. So I want to tell you about some work that I've been involved in the last few years on RKKY interactions. So very briefly, RKKY interactions are indirect spin exchange interactions, usually mediated by conduction electrons. More generally, you could think about mediation by different types of fermions. And the cases that I wanted to talk about involve situations where those fermions are governed by a Dirac equation. I just wanted to acknowledge the various sources of funding for different bits and pieces of what I'll tell you about. So I want to actually start with kind of a pedagogical introduction, just talking very generically about what RKKY interactions are. And I hope this will be useful to the students or anybody who hasn't actually worked on this. It's reasonably straightforward, but there are a couple of things to know. And then I want to go on and talk about how sort of the generic cases kind of change a bit when you're talking about electrons, mediating electrons, being Dirac electrons, and the paradigm for this, for me, are electrons in graphene, and I'll go over this in some detail. And then I want to tell you about a problem that I worked with a student, Jinliu Cao, where there are actually Landau levels involved, so this is a little more relevant to the basic theme of the conference, but those Landau levels won't be generated by real magnetic fields, but rather by pseudo-magnetic field induced by strain, and I'll tell you how that works. And then I want to say a little bit about another setting where there's Dirac electrons, namely the surface of three-dimensional topological insulators, and I'm particularly interested in topological crystalline insulators. And then if there's time, I want to talk a little bit about some of the consequences of the Dirac equation for the spin stiffness and things that can happen because of what happens to the spin stiffness in these systems. I'm not sure I'll get up to this, but we'll see how things go. And then I'll summarize. Okay, I guess I can just use this. Right. All right, so RKKY stands for four authors, these people over here. This work actually started back in the mid-1950s. These two fellows here were interested in interactions between nuclear moments in a metal, and sort of laid out the basic phenomenon. And then these two people quickly realized that the same kind of physics would apply for spin impurities diluted into an electron gas. And this actually, that's the application that has turned out to be much more influential over the years. The basic idea here is that, or the basic ingredients really are that we start with a Fermi gas. So we'll take the simplest example of this, where we have a Fermi gas with two spins, just electrons in 3 dimensions, filling up a Fermi C up to some Fermi momentum. Okay, and then we're going to add some magnetic impurities, typically very dilutely put into the system. And we're going to assume the situation in this game. You usually assume that these magnetic impurities are classical. Usually they have a large spin. And very often at the temperatures you're working at, things like Kondo effect have not come into play yet. Okay, so these impurities get coupled to the electron gas through what's known as the SD Hamiltonian. It's just a local spin exchange interaction with this coupling constant J between the magnetic moment of the impurity and the electron spin density. So that's a very simple kind of coupling. And since we're treating the spins as being classical, we can understand the effect of this term as being kind of a very local magnetic field that the electron gas is being subjected to, right? So here's our kind of effective magnetic field, which here we're really taking to be completely localized. It's a delta function. So the electron gas is going to respond to that. It's going to develop its own magnetic moment. And you can compute that through a spin response function for the electron gas. And since this effective field is very local, we see that when you actually look at the induced magnetization, it's actually proportional to the real space form of the spin response function. Okay, so this is actually the spin susceptibility, another way to say that. So this leads you then to spin density in the electron gas, which actually oscillates. I'll say in a moment where those oscillations come from. but if we put in a second impurity, that second impurity also couples to the electron gas in just the same way as the first one did, and it kind of has to deal with then this oscillating magnetization that's been induced in the electrons from the first impurity, and in this way we get this indirect exchange interaction between the spins. Okay, so this ends up being the RKKY interaction. It looks like a Heisenberg interaction at the end of the day. You notice it's second order in the coupling between the spin and the electron gas. We usually treat that as small. And you can see how it's a function of position, and because of these oscillations, that coupling can have kind of a non-trivial behavior as a function of separation. So where do these oscillations come from? So this is a very well-known phenomenon, and what's very nice about the simple 3D electron gas is that you can more or less work everything out exactly. So that spin response function has a very well-known form. It's the kind of thing that you cut your teeth on when you're taking a first many-body theory class and learning to compute linear response functions. This is one of the simplest ones that you can work through, and it's nice that you can do this analytically. You end up with this, the important working piece of this is the so-called Lindhard function, and you can see it kind of has a singularity when this x, which is this ratio of the wave vector, that's the Fourier transform of the spin response function. So when that wave vector over 2kf goes through 1, there's actually a singularity in this Lindhard function. Actually, it gets singular in its first derivative. And the source of that singularity we can understand very straightforwardly. When we look at what's inside this integral that we have to do, we see two Fermi distribution functions, and what they tell us is that this energy denominator is going to involve the difference in energy between states that are occupied and unoccupied. So we kind of have to be inside one Fermi sphere but outside another one. So if the Q and those Fermi spheres are separated by this wave vector Q, so the states that you actually sum over in this thing then, when Q is small, will be kind of this crescent moon over here. Those will be all the ones that will give you a non-trivial contribution. But then as we increase the Q, you see that these two spheres have separated out, and eventually you get this full sphere. You would use all the states inside this full sphere, and so the kind of joint density states of these particle hole excitation sets that we've made kind of changes its form just at the moment where the blue sphere and the sort of hollow sphere have touched, and that will be when this Q is equal to twice the Fermi momentum. Yeah? Yes, this behavior can happen in any dimension as long as you've got a Fermi surface where there's this sort of touching as you separate them. That's right. Okay, and so that's the reason that we get some interesting behavior at Q equals 2kF. And that's actually the source of these oscillations when you Fourier transform this thing. It's from that singular change in this joint density of states that you actually get these oscillations, and their period in real space is actually, basically it's pi over kF. Okay. All right, so that phenomenon is known as the cone anomaly. Okay. All right, I just want to quickly mention, because I'll use it, another way of thinking about these RKKY interactions, which is completely equivalent. It's really just second order perturbation theory. What we're actually computing when we think about the energy of interaction between these two impurities is how their relative orientation has affected the energy of the electron gas in which they're embedded. All right, and so again, we're treating that coupling, the SD coupling, as kind of a perturbation. So if one goes to second order perturbation theory, you get these matrix elements in a numerator and an energy denominator. There's of course more in the second order perturbation theory in this numerator, but this term and its complex conjugate are the only ones that are sensitive to the relative orientation of the two spins. So you see what's happened is one starts out in an occupied state, then this SD Hamiltonian from one spin scatters you to some unoccupied state, and then the second SD Hamiltonian scatters you back, right? That's a way of interpreting what's going on. And then again, we have this energy denominator involving states that are occupied and unoccupied. Okay. All right, so in any case, we're back to our RKKY interactions between the two impurities. Yes?
Sometimes I confuse it with the Riddle oscillation.
They're very closely related. I think that the underlying mechanism is actually the same. Yes, it's not a confusion, it's a real analogy. That's right. Mm-hmm. Okay. So if the impurities are not too dilute, then you'll be in this region of the spin susceptibility, and you end up with a ferromagnetic interaction amongst the impurities. And this is a way of actually putting impurities into what might otherwise not be a magnetic metal, and turning it into a magnet, actually turning it into a ferromagnet. Of course, if we're more dilute, then we'll be out in this place where the sign of the coupling oscillates. And because the impurities are, of course, randomly placed, the state you would get at low temperatures in that situation would be some kind of spin glass. So for practical purposes, people are often interested in the situation where you have the ferromagnetic coupling dominating the physics. In particular, people in recent years have been thinking about these kinds of things in the context of spintronics, trying to give semiconductors some magnetic properties that might be used. And in this context, in fact, there's an interesting thing to keep in mind, because often the magnetic impurities you put in to your system also will put in carriers. They're charge dopants. And so you end up with a situation where the dopant density and the impurity density, the magnetic impurity density, are tied together. So we're going to see that that does not have to be the case when we're talking about Dirac systems, or the Dirac surfaces that I want to focus on. So this is just a sort of a flash of an example of this. This is lead, I believe this is lead telluride at somewhat low temperature, showing that by putting in, I believe it's manganese, into the material, that you can induce a hysteresis loop. All right, so ready to turn to Dirac electrons. As I said, I want to think mostly about graphene. We've seen slides just like this already in this conference, so let me just establish some notation and go through this quickly. So remember, graphene is a honeycomb lattice. It's important for our purposes to recognize that it is not a Bravais lattice. It's a lattice with a two-point basis. There are two sublattices. When you compute the band structure, you get this sort of famous behavior here with two distinguishable Dirac points in the Brillouin zone. So there are two separate valleys that actually contribute to the low energy physics. And we have this, in the sort of simplest model, we have this very linear dispersion around the Dirac points. And so these are little like light cones. The electrons have a fixed velocity. And one way that this is different than the three-dimensional semiconductors is that you can adjust for a single sample the density of electrons in the system just by making it one of two plates in a parallel plate capacitor. And so by putting a potential on, you can add or remove electrons from the system. So in this system, we can control the density separately from magnetic impurities that you might put in. The other thing to notice is that the Fermi surface can actually change its radius as we change the doping. There'll be some radius out here with some doping, and as I decrease that doping, of course, we shrink to a point when the Fermi energy goes right through the Dirac points, and then the Fermi surface will open again if we continue to change the doping. Okay, there we go. All right, so another point about this that turns out to be important is the fact that the wave functions for the electrons are spinners. There are two amplitudes you have to provide in the wave functions, one for each sublattice. And if we look at the Hamiltonian in the vicinity of one of these Dirac points, you can linearize it and get this well-known, very simple 2x2 Hamiltonian, where the kx and ky are the components of the momentum relative to one of the Dirac points. And this is for one Dirac point. This is for the other Dirac points. Very straightforward to diagonalize these simple Hamiltonians and get the spinners that come out. So the wave functions that you have look like this and this for the two valleys. And if we interpret this two-component wave function as a spinner and look at what the three-dimensional spin is doing, well, the magnitudes of these two components are the same size, so that means that the effective spin is in the xy plane. But because of this angle here, theta k, which is the angle of your momentum with respect to the x-axis, the direction of that spinner in the plane actually winds around as the theta k changes, right? So as you go around the Fermi circle, you see the direction of the spinner, which is the blue arrow here, actually go around by 2 pi. So this has interesting consequences, a variety of consequences. Very well known, for example, that graphene is an excellent conductor. And one way of understanding that is the fact that this wave function, if we're in conduction, one of the most important in the presence of not spinful impurities, just regular impurities, One of the most important limitations is backscattering of the electrons, but because you've got to flip your spin when you're going from one side of the Fermi surface to the other, the wave functions associated with the blue arrows are actually orthogonal to one another. So this is saying that, that backscattering in graphene is actually suppressed because of this wave function phenomenon. And this is the reason that impurities are not quite so effective in graphene as in other materials. It's the reason it's a good conductor. Okay.
Attaining is always separates in the Archangel liquid is in the graphene is always in the Archangel liquid phase.
It's not Lunger liquid. This is a two-dimensional material.
Still, it is always in the metallic state.
Right. It's very hard to localize electrons in graphene. If it happens, it has. You have to get, so if we're talking about the non-interacting limit, you actually have to get scattering from one valley to the other to really localize the electrons. Now that does happen, but it's sort of at a much lower level than the intra-valley scattering, typically. Okay. All right, and so another thing to keep in mind is that the spins in our system can be in different locations in the graphene lattice, and this turns out to make a difference. So in many cases, the spins will actually, the impurities will actually be chemically bonded to the carbon atoms, the underlying carbon atoms, but we have to recognize that they can be on an A or a B sublattice site, and so the response will actually be sensitive to whether your two impurities are in the same sublattice or different sublattices. There are also situations for some types of chemicals where you might have your impurity in more symmetric locations. There are a few that end up sort of on these bonds over here, and some can even end up kind of in the hole of the hexagons in the graphene. So the difference then in the spin response that you would look at for graphene from what I showed you in the standard case, basically is just kind of a wave function overlap that we didn't have to deal with. It was very trivial to deal with before. So those wave function overlaps, they're very simple to compute, but what's important is that they're different depending on whether the two impurities are in the same or different sublattices. And so we can see because of these overlaps, we're going to get different results for the two cases. But they turn out to be very closely related to each other. Okay. The AA response, right? Two impurities on the same sublattice, so we call that AA, is different than opposite sublattice, AB response. Okay, so we'd be thinking about, say, two impurities like these. It's convenient to write your response function as a part for zero chemical potential plus a correction that you can put in if you dope the system. And these are just some kind of qualitative pictures of what these different pieces look like. The chi-AA 0, when it's undoped, is very simple. It's just a straight line. And this correction here, when we put in the doping, well, this actually has the cusp in it. Okay, it has the cone anomaly in it, right? And so the position of that cusp will depend on what your Fermi energy is, or what your Fermi wave vector.
Sir, why it is called anomaly?
Why is it called, say again?
Why it is called anomaly? It's the usual factors.
I don't know where, that's a good question. I don't know where the name came from, but that's, yes, it's what you find it's what you find in textbooks. When it was first discovered, it seemed anomalous to people, I guess, but now we're kind of used to it, right? Mm-hmm. All right. Good. All right, so in particular, you can look at the effect of the cone anomaly directly on the spin response function, and you find that just the cusp piece will give you something that oscillates. That's not surprising. We've seen that already. And that oscillation is in this two-dimensional system, turns out to be in an envelope that falls off as 1 over r squared. In the three-dimensional system, it actually fell off as 1 over r cubed. So that's contrasted with the situation when we have impurities that are more symmetrically located. Basically, you can convince yourself that the relevant response is just an equal weighted average of the responses for the two sublattices, responses on same and different sublattices. And when you add these together, it works out that the cone anomaly becomes much more subtle, and that's because of this backscattering phenomenon, right? So there is an anomaly here at 1, but you see it's not quite the cusp here. The slopes join together continuously. You have to go to a higher order derivative before you can see there's a singularity. And that ends up it still gives you oscillations, but they fall off more quickly with this distance, right? So in some sense, they're less obvious at large distances. And so the fact that this is smoothed out comes from the fact that when we scattered from an occupied to an unoccupied state, the spin has actually flipped from one direction to another. So again, this wave function overlap ends up vanishing just at the point where that singularity was supposed to give us the oscillations. It doesn't go away completely, but it's suppressed. Okay, is that clear? Okay. Good. All right, so the result of this then is that the responses on same and opposite sublattices are almost equal and opposite. Actually, it's the singular part that's equal and opposite, but there is some correction between the two of them that behaves smoothly. If we look at just the singular part, though, we see, again, in real space, these are, again, equal and opposite. And what's nice about this is that when we're close enough, when the impurities are close enough to be ferromagnetically correlated on the same sublattice, they'll be antiferromagnetically correlated on opposite sublattice. And so we get antiferromagnetic correlations, right? So the A sublattice will have spins in one direction, the B in the other when we're in the low, in the low temperature state of the system. Okay, and so it's nice you get this antiferromagnetism without invoking any Hubbard U or anything like that. This is all from non-interacting physics. Right? We can also go to the situation where the graphene is undoped, so the KF goes to 0. So these coupling constants don't go away. They fall off as 1 over r cubed. And another thing to know about the result is that these are equal and opposite, but not just up to some correction. The responses are exactly equal and opposite in this case. Okay. All right, so to check some of these things, we did, particularly, we've been using a continuum model, so to sort of check that this really works in the microscopic model, we did some tight binding, sort of simple tight binding calculations. We considered a system that's kind of infinite in one dimension, but imposed periodic boundary conditions in the other dimension, so effectively the system is actually kind of a nanotube. And then looked at the spin response of the electrons in response to a local magnetic field placed on only one of the two sublattices. And what we actually did was put that local magnetic field on one, basically on a line sort of encircling this nanotube, so on a single line, and then looked at the response as you moved away from that line. Okay. Yeah, Yuval.
Next year's table, or next year's table, from 2 weeks to be significant?
Yeah, we're just ignoring them here. So near the Dirac cone, those tend to be. You're asking about the hopping in the graphene lattice. Yeah, so I mean, that can be included. That has the effect of breaking particle hole symmetry, for example, if you take the next nearest neighbor. But near the Dirac point, this seems to have very little effect. Yeah. Okay. So you want okay, so if they're talking about neighboring impurities and then next nearest neighbor or something like that. So what exactly is the question?
So RKKY has
oscillation. So if they're very dilute, okay, so you could end up with some collective state that's very complicated. So I'm mostly thinking about the situation where they're not that dilute and the ferromagnetic part is dominating. Right, so people have been interested in trying to give graphene magnetic properties for similar reasons to what people are doing with dilute magnetic semiconductors. So that's the limit people care about. Okay, so we put in these sort of localized magnetic fields to look at the electron response. And there are a couple of interesting things that come out of this. So this is showing the magnetic response when you're undoped on the A and B sublattice. So the red sublattice is basically where we put the field, the black one where we didn't put the field. The spin responds in the direction you'd expect on the A sublattice, let's say, and you see the B sublattice is indeed responding in the opposite direction. The other thing that's interesting about this is if you add up the total induced spin in the entire system from this local magnetic field, even though there's a net magnetic field, the total spin that you induce turns out to be 0. And that's actually the fact that this chi-AA and chi-AB are equal and opposite, so that when we add them together, at Q goes to 0, they actually go to 0. You get no response at Q equals 0. And that contrasts with what happens when we start to dope the system. If you look carefully in these parts over here, you can see the 2KF oscillations. Overall, the basic response looks very similar to the undoped case, but if you add up the total spin, now indeed you get some response. So it's only for the undoped system that there's this exact cancellation between the two sublattice responses. And of course, the total amount of charge, of spin that you induce, for a given magnetic field on one of the sublattices increases with, increases with the doping of the system. All right, so here's my one slide I think is most closely relevant to the conference. This is actually looking at a real ribbon with edges on it. Here we've done a couple of examples where we put magnetic field at the edge. In this case, it's on just one sublattice, and you kind of see this antiferromagnetic response. So the field is applied over here. But what's interesting is, so we've applied the field to induce the spin on the black sublattice, basically. You see the antiferromagnetic response on the red sublattice, and some of it is here in the original, sort of the side where you put the field, but on the opposite side where there's no field, there's a very large response. So that's sort of an interesting thing that can happen in graphene. You get this strong spin responses at the edges. And I should say these are so-called zigzag edges. It is important that to get this sort of behavior, that at one edge you have, let's say, the A sublattice, and the other edge you have the B sublattice. That's part of the reason this comes out the way it does. Okay. Again, even with the edges present, there's no net spin response in the system. The total induced spin is 0. Here we put a magnetic field that is sort of anti-symmetric, so same field on one edge as in the other, but in opposite directions. Again, no net spin response from the system as a whole. But then if we, here we put the two magnetic fields in the same direction. I believe this one is doped, and the total spin induced is not 0. Yeah. So we didn't do a lot of studies of that, but I think it's pretty robust. It will survive. I don't want to quite say to infinity, but I think that's actually possibly right, that it would survive all the way out. Mm-hmm.
Is it not decaying like 1 over r squared?
Not 1 over r squared here, because this has kind of been, it's a line of magnetic moments, so it would fall off as 1 over r at best, I think. But we didn't look at that carefully, so I'm not really sure. All right, so that's the picture that you get from just graphene. I wanted to now turn to a somewhat different problem. As I said, people are interested in trying to put together magnetic properties with graphene and see if they can do some kind of spintronics with it. That's one of the driving forces behind. There's actually a lot of work, I should say. I haven't given you references and such, but there's quite a number of people who've worked on these various problems, mostly in the theory community, I should say. But in any case, one of the things that hasn't worked out well is to actually get something that you can really measure, a magnetic moment you can measure, because with an antiferromagnetic response, that's hard to see the magnetic order in any direct way. So it would be nice, given what's driving all the research, if we could actually get a ferromagnetic response out of graphene. And we had an idea about how that might be done. That sort of works, but we'll see that there's some significant limitations to what happens. So the idea here was to introduce a magnetic field using strain. And the reason we thought this might work was, you'll notice that we get this this sort of perfect antiferromagnetic response because of the symmetry between the A and B sublattices. So we thought if we can do something that breaks that symmetry, maybe we can get a ferromagnetic response, or a ferrimagnetic response, maybe something that's mixed antiferromagnetic and ferromagnetic. So the way this could be done was actually first pointed out about 10 years ago now by Paco Ganiya and some of his coworkers. If you strain your graphene in a particular way, you actually can create kind of effective magnetic fields inside the graphene. So for example, for a 10% strain, you can get something of the order of 40 Tesla. So these fields can be rather large. And I should say that graphene can put up with a 10% strain without ripping. Okay? And it's very important to recognize that if we put in a magnetic field just by, it's not really a magnetic field. If I just simply strain the system, I haven't broken time reversal symmetry. And the way the time reversal symmetry is respected is by looking at what happens at the two valleys. In fact, the magnetic fields are oppositely oriented for the two valleys. So the two valleys are actually time reverse partners of one another. If we flip the field going from one to the other, we actually have a system with overall time reversal symmetry. Nevertheless, each valley does have this magnetic field, and so there are Landau levels. The spectrum kind of breaks up from the Dirac cone into a set of discrete Landau levels. So let me just quickly tell you what happens to our wave functions in this situation. So rather than have just these simple phases that I showed you before, we now end up with magnetic states that actually look a lot like what Ganpathy showed us in his very first lecture. These are harmonic oscillator wave functions multiplied by a phase factor. The location around which these harmonic oscillator states are localized is tied to that wave vector in a well-known way. And what's interesting for the graphene situation, for the graphene setting, is that the Landau level index or the harmonic oscillator index is different depending on which of the two sublattices you're talking about. And in particular, because these differ by a single unit, if you go to the kind of the n equals 0 case, well, there's no phi minus 1. So actually what happens is one of the sublattices has no support for the n equals 0 case. Now, all values of n, both positive and negative n, 0, are allowed. The energies have this form over here. You notice that the energies of these states are not linear in this integer n. It goes as square root of n. So sometimes this is sort of an example of how people sometimes say that the Dirac equation is the square root of the Schrodinger equation. And this is a direct way of sort of seeing that. So in any case, we get these highly degenerate Landau levels of both positive and negative energy. And because of the square root over here, those Landau levels get closer together as you get away from 0 energy. And again, the other thing that's interesting here is that 0th energy Landau level. The way I've described this, of course, there's clearly an imbalance between the two sublattices. In a real magnetic field, the way that imbalance is corrected is by looking at the other valley where the two sublattices switch roles, and then you basically get overall in your Hilbert space, you get the two sublattices treated in just the same way. Okay. All right, so now each of these Landau levels, remember, has a very big degeneracy. Again, this was described to us in the very first pedagogical lecture. But it's also important to recognize, because of the two valleys and the two spins, that the number of states in each of these Landau levels is actually 4 times larger than what you would get for a single Landau level. Okay. All right, now in the pseudomagnetic fields, the wave functions for the two valleys, rather than being kind of interchanged with respect to the two sublattices, they're actually the same. Right? So one of these two cases no longer appears, and that's because we changed the direction of the magnetic field when we went from one valley to the other. So now we really can see that indeed the two sublattices are going to be treated differently. So maybe we can get some ferromagnetism in this case. Right?
So in the real magnetic field, the 0 Landau level, different values do not mix. I mean, you have either Landau levels on sublattice A or sublattice B. In
the 0th Landau level.
Zero. In the non-zero Landau levels, they mix.
Yes.
What happens with this pseudo?
So it's just the same, except you just simply have one, you have sort of two sets of wave functions that look like so. And of course, they're multiplied by a rapidly oscillating piece that I'm not showing that has to do with the center, where the valley is centered, right? So they both look like this. They are not mixed in the n equals 0 Landau level.
But the weight, I mean, let's take n non-equal to 0. The weight of sublattice A is the same as the weight of sublattice B?
Yeah, so if you integrate this, right, square it and integrate it, right, the total weight is going to be equal for the two sublattices, right? But the spatial wave functions are different, right, for the same n, right? And n equals 0, that's the one and only case, right, where there's only one only support on one sublattice. Okay. So that point actually suggests what's shown over here, that we're going to actually get some contribution when we start talking about RKKY interactions between impurities that are on, let's say, the blue sublattice over here. That is a contribution that won't appear when they're on the red sublattice, because we don't have any support on the red sublattice in one of these Landau levels. Okay, so again, we can see how a difference is going to arise. Okay, now, there's a challenge here in doing the calculation that makes us move away from the standard way of doing it. And it's a standard problem that you get in second-order perturbation theory, right? So if we're doing second-order perturbation theory, and I've got a Landau level, if I imagine that the graphene is undoped, I've got a Landau level that's only partially filled, then the sum I have to do here involves states that are unoccupied and occupied at the same energies, and we get a divergence, right? So as often is known, when you're doing these problems, these quantum Hall type problems in Landau levels, perturbation theory really just doesn't work, right? So we need to deal with this. Our strategy was actually to go back to this very basic formula that actually underpins the spin response formalism that I told you about at the beginning, and look for the energy of the electron gas in the presence of these impurities. And what I want to show you, I think it's kind of a cute trick, that you're actually able to deal with this zeroth Landau level basically exactly. We're able to figure out the spectrum. If we project into this Landau level, we can figure out the spectrum exactly when I have two spin impurities present, and then we'll be able to deal with all the rest of the Landau levels perturbatively in the usual way. Okay. So here's the trick. Okay. Now we're going to go to Jainendra's lecture, reminding ourselves how you write down states in the lowest Landau level. If they're on a disk, we might have capital M states. They have this form with the index M, which is the angular momentum, and the positions are represented in terms of this complex notation. Okay. Now, I can actually identify states that will be completely unaffected in their energies by the impurities. Remember, the impurities are very local. They're sort of delta function localized. So if I construct states where the impurities, which I'm writing, whose position I'm writing in this complex notation, if I write down states of this form, you can see that the wave function will vanish at the location of either impurity. Right? And so these states can't tell that the impurities are present. Their energy is going to be completely unaffected because remember what Jainendra told us, that if you have an analytic function of z times this Gaussian factor, you are in the lowest Landau level. The kinetic energy is going to remain 0. Okay? So we can ask ourselves, well, how many such states can I make? You can convince yourself that the number of independent states is actually going to be this m minus 2. Right? And so what I know there's capital M, I know that there's capital M states in total in this Hilbert space. So I need to look for two states that do touch the impurities. And the way this proceeds is you actually take two states and you write out an expansion as a power series in the Z's. You demand that those states are actually orthogonal to all these states. You end up producing a recursion relation for the coefficients of this polynomial expansion. And it turns out it's very nice. It turns out in the limit that m goes to infinity that you actually sum the coefficients and you discover they're basically a sinh and a cosh. All right? So we can write down these two wave functions exactly that are actually touching the impurity. So there are two such states, or two impurities, I should say. So there are two such states for a given spin. This is a spin problem, so we need to write down the copies of these for the other spin. And so the Hilbert space I have to deal with is actually just four-dimensional, right? And that's it, right? And so we just plug in our SD Hamiltonian to that four-dimensional space. It's a 4x4 matrix equation. You ask Mathematica, what are the eigenvalues, and it tells you. And they're kind of a mess, but you have the answer. Okay? So I'll just show you pictures of what things look like. So this is the energy of those four states as a function of the separation. Actually, this is twice the distance in units of magnetic length between the two impurities. And on this axis, this shows you that the relative orientation of the two impurities will affect the energy of the states. So basically what we've done is we've developed two bound states for the two impurities. So now our picture of the spectrum looks something like this. Right? So my chemical potential, again, is through the n equals 0 Landau level. I've occupied these two states over here, and their energy depends on the relative angle as well as the separation. So it's interesting to notice, first of all, that this is, again, it turns out to be a ferromagnetic interaction. The energy of these two things is summed together is lowest when the two spins are aligned with each other. It's a relatively strong interaction because it's linear in the coupling. Remember, we take that coupling to be small. But this is a non-analytic contribution to the RKKY interaction. So it's a strong, it's a strong coupling. Yes? So this is the sum of these two energies over here, basically the two occupied state energies. Okay? So it's a strong interaction, but I should point out that it falls off relatively quickly. It falls off as a Gaussian. Not surprisingly, when we're working with states in a Landau level. And that contrasts with the situation from no magnetic field where the coupling actually fell off as 1 over r cubed. Right? So it's sort of weaker, but it was much longer range. So these things, yeah, Ganpathy. A lot, very good. This is a point I have to come to. right? In a typical situation, there are many impurities in there. Good. Okay. All right. And then let's remember this is acting not on both sublattices as contribution, but only on spins that happen to be on the same sublattice. Okay, so that was the contribution from the 0th Landau level. We have all those other Landau levels. So this we can handle with standard perturbation theory. Take that that contribution, that form that I showed you before. This is now written out for the quantum numbers relevant to Landau levels. And there's details into actually doing this sum. Actually, it's very nice that you can kind of sum everything up. You can find analytic ways of kind of integrating over the momenta. You can sum everything up until you get to the Landau level index itself. Then we kind of got stuck, and all we could do was sum that numerically. But that's, you know, a few thousand terms. That was not hard to do as a numerical problem. And so Jinliu really did this. The student did this. And so we could look at this contribution as well. We were looking at sort of the difference between, or how this response for the A and for being on the same sublattice and being on opposite sublattices. So once again, it's got this antiferromagnetic correlation, right? These are different, these are the same. And you notice, of course, the oscillations here. The reason for these oscillations turn out to have to do with the cutoff in my Landau level indices, right? So remember, every Landau level has some number of electrons in it. If I try to sum all the way to infinity, I'm actually going to get a divergence because I would actually be saying there's an infinite number of electrons in the system, and that's not true. So I have to cut these off, these Landau level indices off, so I get the right number of electrons in the system. And so you can figure out what that cutoff is for a given magnetic field. And we use just a hard cutoff to do this. That hard cutoff is what leads to these oscillations. I suspect if we did something that had a softer cutoff, we would lose them. But I think they're not very important in any case because these impurities are kind of randomly located. So where exactly you are in these oscillations are going to get kind of averaged over anyway. The overall trend, though, is the antiferromagnetic coupling on opposite sublattices and ferromagnetic on the same sublattice. And one thing that's interesting about this is that if you look at the tail, if you look at the tail of this interaction at very long distances, if you throw it on a log-log plot, you discover that the fall-off is basically 1 over r cubed. It's still depending as a function of distance in the same way as what we had without the magnetic field. Okay. All right, so to get some basic idea of what the effect of this extra term might be, we thought to do a mean field theory for this system of impurity spins. And naively, what you would want to do, and where we started to head, was to think about pairwise interactions between the magnetic impurities. So we don't look at the electrons necessarily directly, but just look at the the SS coupling between the impurities. And you'd want to do just a standard mean field theory, right, where you you freeze all the spins except one to their average, and then you look at the fluctuations of the one spin and the average field of all the others. But we quickly realized that there's a problem with doing that in this situation, and it comes back to what Ganpathy said. The density of impurities in the system is actually very large compared to the density of electrons in a Landau level. Right? So the way things were working and what I showed you, you got some bound states introduced by the presence of the impurities. So the impurities were binding some electrons. But now with this number of electrons, I have far more impurities and electrons available in the lowest Landau level. They can't all bind impurities. There's just not enough electrons available. So what we thought to do then is, again, we're just trying to get estimates here. So we did a very simple mean field theory. We imagined that only some portion of the impurities actually have electrons from the lowest Landau level bound to them. Right? So we'll say some fraction determined by the density of electrons in the lowest Landau level are binding impurities on, let's say, the B sublattice. And then all the others, which is actually most of them, will not have these extra bound electrons. And then we can just work that very simple problem of this impurity binding a single electron from the lowest Landau level and add that energy to the energy of these sites in the lattice. So it's actually simpler than what I showed you, but it's very analogous to what I showed you for the 2 impurity problem. All right. So once we do that, we can, and of course the A sublattice does not have these extra electrons. That just has this 1 over r cubed coupling. All right. And so again, really Jin Liu, the student, worked through this. So these are the A and B sublattices. This is the sublattice without the extra impurity, without the extra contribution from the lowest lambda level. This has the contribution from the lowest lambda level. You see how this part, these are the impurities though, these are the impurities that don't have the contribution from the lowest lambda level. What is this telling me? Okay, I see. All right, so in any case, so you see how the magnetization as a function of temperature is dropped down. It looks like it wants to go to 0, but it doesn't really quite do that because those sites that actually have the extra electrons actually will keep their magnetization out to a much higher temperature, right? So there is some magnetization here, but it's very hard to see. But the magnetization from the extra electrons is actually, you can see that on that fraction of magnetic impurities. So we've succeeded at getting the ferromagnetism. That's what we wanted to do. The problem is that there's so few of these impurities, right? So if you actually work out the net moment, it actually works out to be something very small. And so, so formally we've succeeded at what we want to do, but this would still be very hard to detect because the moment you induce while it's present is still a rather small thing, okay? All right, so this is what I want to say about graphene. Did anyone want to ask anything? And I'll just flash a couple of slides and then I'll stop to say about what happens in topological insulators. Okay, so let me just then turn to this sort of setting, which is, again, this is the surface of a topological insulator. This is a generic kind of introductory slide to that. We know that three-dimensional topological insulators have their own edge states, but they're really surface states because the edge is a two-dimensional surface. The topological insulators, in sort of the paradigm of this, will have some protection from time reversal symmetry, which guarantees that there'll be some point on a surface, for a surface state, that will be a Kramer's doublet, will be doubly degenerate. And so if you go to the surface Brillouin zone for some particular surface of one of these topological insulator surfaces, you discover there's a Dirac cone, one or more Dirac cones associated with that surface. All right, so this is another place where we can get interesting RKKY interactions. Again, there's quite a number of papers on the subject. A number of people have looked at this. I'm not being very fair about showing references. I'm just sort of trying to show you the things that we've been involved in. So there's a couple of differences from graphene. One important one is that the spinners that make up the two-component Hamiltonian for the Dirac equation, or that the Hamiltonian is acting upon, actually directly contains spin content. Right? With graphene, the spin was a separate degree of freedom. Here, the spin is actually in the two-component spinner itself. And it turns out that the coupling of magnetic impurities, because of the strong spin-orbit coupling in these materials, the coupling of the magnetic impurities to these Dirac electrons can be kind of complicated. Okay. So we can kind of run through things in a way that I described, similar to what I described before. So actually what I want to do here is kind of sort of almost start out at the mean field level by treating these spins not as individual entities, but just imagining that their spin is some spin field or sort of effective magnetic field that is a function of position, right? So I'm just averaging over the spins because they are actually pretty close together. Okay, so if we do that for the graphene case, you would end up with an effective Hamiltonian that looks something like this. The sigmas, again, are acting on the sublattices. You notice how this difference in the magnetic fields for the two sublattices comes in. It has the opposite sign for the two sublattices. And you can already see why antiferromagnetism is favored in graphene, because what will happen is that if I take a spin configuration where this is not 0 and this is 0, well, I'll introduce a mass term to my Hamiltonian. And by introducing a mass term, I will take these states here that were previously filled. They're still filled, but then push down in energy because of the mass term that you've introduced. And so it lowers the energy to configure your spins in such a way that you get antiferromagnetism. Okay? So the difference with topological insulators is now we're going to have that field coupled directly to the spinners rather than through this coefficient that's acting on a separate degree of freedom. And that means actually that the different components of the spin are going to come in differently. Some components will actually simply move around where your Dirac point is, but there is always a component that will open a gap. And this component here is actually a component that breaks whatever symmetry is protecting the Dirac point in the first place. If it breaks the symmetry, it opens a gap. Okay, so this means that particular directions for the magnetic field can be picked out in a way that wasn't true for the graphene setting. Now, where I thought we kind of thought this was very interesting, or most interesting, might be in a system like this topological crystalline insulator. I don't think I have time to go through all the details of this. But what's nice about this is that this has more than one such Dirac point. I'm getting a hint here to wrap up. Okay, it has more than one such Dirac point. In fact, if we take the so-called 1-1-1 surface, there are 4 Dirac points. And you can look at the competition amongst those Dirac points on the way the spins order. So let me just quickly tell the answer to that without going through the details. So what happens is you find that when you line up your, so what happens is that these Dirac points come in a group of 3 and a single isolated Dirac point. The 3 are lower in energy than the isolated one. If you put your chemical potential near the isolated Dirac point, then there are 2 favored directions for the spin. And they turn out to be either perpendicular or anti-perpendicular to the surface. Whereas if you put your chemical potential near the other 3, those favored directions turn out to lie near the plane. There are actually 6 favored directions. I'm showing you the block sphere here. So there's 3 more directions I can't show you that are on the other side of the Dirac sphere, so the block sphere. So this is to say that now we can go from a system, it's actually the same system, we can go from something that has sort of a 2-fold manifold of low energy directions to something that has 6 different possible directions. And if you're thinking about thermal disordering, for example, that can be interesting because the thermal disordering are in different universality classes for these 2 cases. And what's nice is you can get to those different universality classes just by changing the density of electrons, in principle by just gating the sample and changing the density, and you should be able to adjust which type of thermal phase transition you get. All right, so I'm out of time. I'm not going to talk about spin stiffness at all. Let me just flash one more slide here with my various collaborators. And this is actually some of the things I told you about have taken place over a fairly long period of time. This is a summary and the various papers that are relevant to what I told you about, so I'm going to stop. Okay, thank you.
Let me perhaps start with an experimental
Yeah, okay.
When you apply strain on the graphene, your analysis relies on the fact that the strain is uniform throughout the sample. How is this guaranteed, or to what extent?
It's not guaranteed. So there's some experimental realizations of this. It's almost impossible to get a truly uniform. And I think what actually this means is that the effective magnetic field is really a function of position in a real realization of this. But we should remember that the impurities are kind of very close together on the scale of the magnetic length. So I think it's okay for one to imagine a fluctuating magnetic field, right? Where the effective coupling amongst the impurities is.
The non-uniformity is on scales much larger than the lattice space.
That's right. That's right. Right, because you're straining it, so the strain is spread out over many, many lattice constants, whereas the impurities, so if we talk about a 1% thing, so there's maybe 10 lattice constants or something like that between impurities, which is still a very small distance. So you're imagining the strain is not on the scale of the lattice constant, but it's a much longer length scale.
So if I think of a sort of a caricature where certain area of my lattice has one strain and another area has another strain, I would have some boundary. Here, of course, you don't have a boundary because everything is smooth.
Right.
But how do you treat those non-uniform pseudo-magnetic fields?
So, I mean, you can. I mean, so maybe the most interesting example of something like that would be if you have oppositely directed magnetic fields. I'm sure you could set up a strain field in principle to do that, right? And then you get snake states, for example, in between those. So, right, so that would give you some interest at the boundary between these two things. You get some interesting coupling amongst the impurities. So I don't know anyone. I haven't worked that. I don't know anyone has done that, but that could be interesting. Yeah.
So I want to ask you that can anyone from using the dimensional counting can say that the RKKY interaction between the sublattice should be form of 1 over r square? Or
I think the 1 over r squared in the doped case, I think it's just the same as you would get just for conventional electron gas. I think it is just from the dimensionality of the system that it falls off that way. Right? So what's a little bit unusual and interesting is that 1 over r cubed when it's undoped. Yeah. Sorry, yeah.
My question is, when you strand the graphene, is magnetic field induced, which is pseudo-magnetic field uniform?
We're assuming it's uniform. That's very, as I was saying to Yuval, that's very hard to do in reality. The closest they've come that I'm aware of is actually, it's in Harry Manoharan's lab. It's not really graphene though. They take these carbon monoxide dimers and put them down on a substrate and in a way that forms that strain field, and it's an analog of strain graphene, but they've done this pattern that Paco Ganilla first came up with, and it's indeed, it looks very much, if you look at the density states, which they can measure with tunneling, it does indeed look like a uniform magnetic field. But that's not a very interesting example for our purposes, because why would we want to dope that with magnetic impurities, right? It's the real graphene we're interested in. So people kind of do the best they can. Another setting where this is done is actually placing the graphene onto some kind of substrate where there might be impurities or bumps and wiggles of some sort, so that there are local regions that are strained. So you might be able to get local regions where you've induced this ferromagnetism. So that may or may not be useful, but that's a way to do it. But it's very hard to actually get truly uniform. We've assumed it's uniform for the simplicity of the problem, but it's hard to get that in a real sample.
Also, when you construct the wave function of lambda level, it seems that you are assuming some form of wave function is like in the uniform
magnetic field. That's exactly what we did.
Also, since here is a lattice, however, the wave function, the phi 1, those seem to be a wave
Continuum.
function.
Right. We're assuming
Continuum.
that we're assuming that we're in a limit where the microscopic scale, the distance between carbon atoms is very, very small compared to any other length scale in the problem. And so we go to a continuum limit to deal with that.
Okay,
And that's the wave functions I showed you.
Thank you.
Are there any experiments on the crystalline topological?
She's asking if there's experiments on the TCIs.
On the TCIs, the magnetic impurities.
So
yeah.
people have tried, and there's actually some technical problem, I've been told, that they don't really understand, and I don't know how hard people are working to solve it, but it appears that when you actually put in the magnetic impurities in the TCI, it closes the gap. Again, they don't really, you don't get that from the DFT calculations apparently, so they don't know why exactly that's happening. I should say in these materials, these are actually, the first picture I showed you of a dilute magnetic semiconductor is closely related to the TCI materials. That's actually lead telluride, what I showed you, right? And it's tin lead telluride alloys that are the kinds of materials that I was talking about when I was in the TCI context. So they dope these things, they make them into nice magnetic semiconductors, but to actually get it into the topological regime, there's some problem. And again, it's not really understood what the reason for it is.
You mentioned that the number of magnetic impurities often exceeds the number of states in the lowest Landau level. So in that case, is it at all justified to treat two impurities at a time, or you actually need to solve in the presence of all of them?
Right, so maybe that went by quickly, but when we did the mean field theory, we did not deal with them two at a time. I mean, so one could imagine very dilute impurities when what I was talking about would be okay. And so sort of more straightforward analysis would work, but again, you'd end up with a tiny magnetization because the impurities would be so dilute. Yeah.
Any more questions?
Yeah.
Sorry if you mentioned this before, I missed it. What are the typical magnetic fields that will be generated by these strains?
By the strain field?
Yes.
Yeah. So something like a 10% strain gives you a 40 Tesla field. So Michael Cromie has done some experiments in this setting that I mentioned answering the previous question so he put the graphene on top of some kind of bubble. I don't remember exactly. It was some impurity. So he put on a substrate with an impurity, so it was locally strained. And there he could measure a Landau level spacing that would actually correspond to 300 Tesla. So you can make it pretty big, at least locally.
Okay, I see no more questions, so let's thank Herbert again.